Our last video with the definition of a Riemann sum. Let's actually work out a particular example of calculating a Riemann sum. So the function I want to work with is f of x is 8 plus 12 sine x minus 4x. And we want to find a Riemann sum on the interval from 0 to 4 using 4 subintervals. And so let's say the places that we're chopping are 1, 1.8, 2.9, and 4. So we can choose any numbers that we want to in between 0 and 4 to do this. They don't have to be equally spaced here. We see that the differences here, delta x1 is equal to 1 minus 0 is 1. Delta x2, these are all going to be the widths of the appropriate rectangles, 1.8 minus 1. Delta x3 is equal to 1.1. Delta x4 is equal to 1.1. Not only that, but we also have to make choices for what point to use as providing us with the height of our rectangle. So I've made those choices over here. C1 is 0.4, C2 is 1.2, so on and so forth. We could choose any number in between 0 and 1 here that we want. We can choose any number in between 1 and 1.8 that we want. These are the decisions that I've made. So we've got all the information that we need now to write out what our Riemann sum is. So for the first rectangle, so delta x1 times f of c1, and so delta x1 is 1, and f of c1, if you plug in 0.4 up here for x, you end up with, I guess I don't have that pre-computed here, so I just say 1 times f of c1, and then you would do 0.8 times f of c2, f of 0.4, f of 1.2, plus 1.1 times f of 2, plus 1.1 times f of 3.5. And so I do have this. If you do this calculation, plug all this stuff up here, you end up with something that is about 23.35. So that's an example of calculating out a Riemann sum. So at this point then, we are ready to write down our definition, our most important definition for this section. So a function is integrable on the interval a to b if every single Riemann sum approaches one and the same limit as we make the norm of our partition. Remember this norm of p here, that's the width of the largest partition, the largest subpartition here. So in this case, 1.1 would be the biggest. As the largest subinterval gets smaller and smaller as it tends to 0, we say that this function is integrable. Every single Riemann sum goes to the same limit, and this limit is called the definite integral of f over a to b. And so we say here, the notation here is f of x, there's a little integral sign, kind of elongated s there, integral from a to b of f of x dx. So no matter, so what's going on here, we want, in the previous video, once more, we said that if our function is continuous, both endpoint approximations and the midpoint approximation all go to the same limit as n goes to infinity. This is saying here, for the Riemann sums, I missed an extra n there in Riemann, that's saying that all of these Riemann sums, the endpoint and the midpoint approximation, these are special cases of Riemann sums, but every single Riemann sum goes to the same limit no matter how we chop up the intervals. So that's our definition here of f of x dx, and this is me writing it out in notation here. It just expresses what's going on. So this is our definition of the definite integral. We should say here some notation, some commentary here, integral from a to b of f of x dx. This we can just call this an integral. f of x dx this is what we call the integrand. A and B are what I would call bounds on our integral. Or sometimes, I guess the textbook prefers limits of integration. This x here is what we would call a dummy variable. So if we want to say the integral from a to b of x squared dx, this is the same thing as writing an integral from a to b of t squared dt. This is the same thing as the writing an integral from a to b of u squared du. We can use any letter basically that we want to there, and it all expresses the same idea. Okay, some other comments here to make is that if we have a continuous function, or if we have continuous except at finitely many jump discontinuities, then our function is guaranteed to be integrable. So finitely many jump discontinuities, let me draw an example of a function like that. So this function from here to here has two different jump discontinuities. Other than that, it's continuous. So this theorem is guaranteeing that this theorem guarantees for us that our function is in fact integrable. Okay, so at this point we want to start thinking about what are some actually answers here to our definite integrals. So the first function that we're going to say here is that, let's think about what happens if we integrate from a to b k dx, where this k is a constant. Well, if we draw a picture here from a to b, no matter how we chop up our interval here, our rectangles are always going to have height k, and the overall sum of the lengths of the rectangles is going to be the length from a to b, b minus a. So no matter how we slice it, the area here is going to be b minus a times k, and so that is going to be the answer for this definite integral here. Okay, I think that's a good place to wrap up this video. In our next video, we'll do some more examples of calculating out definite integrals.